talk about electron configuration. So we'll start off by just reminding ourselves from yesterday about the idea of the principal quantum number. The electron orbital in which an atom can be found is called its principal quantum number, n. Because of Bohr's work and the work of many others, we've learned that each orbital can only hold a certain number of electrons. We'll remind ourselves of that. So if we have the nucleus here, I want a nice perfect circle. Oh, much better. Whoa, okay, actually, no, I don't love it. Actually, I don't want to take it back. Sorry? I'm doing my best. We have n equals 1, n equals 2, n equals 3, and n, and they do keep going. All right. In theory, you could have, if an electron had enough energy, it could, in theory, go into any level of orbitals. In practice, we're going to see that there's a practical upper limit, but there's not a theoretical upper limit. So we have different orbitals. Remind me, the first orbital, how many electrons did we say it can hold? What about the second orbital? Okay. And the third? Okay. So we're going to talk about that. And then we go from there, right? This has always been kind of our, we'll get there. So, yeah.
So what if, like, you go with an element like, I don't know how to pronounce it, magnesium, where it's like 118. It's got a lot of cells.
Yeah, we're going to talk about that today.
Like, did they go even further out?
Some of the cells have 64.
Yeah, that's right. So we're going to talk about it. So here's the basic idea, and this is where we're going to get going. For each shell, for each principal quantum number, for each orbital, there are a number of what we call subshells or suborbitals. For each subshell is given a number L. Okay? So this is the equivalent address. For example, if you go on any street in Welland, there's a number of houses, right? So if you were going to give your address, you would give the street number you're at, and then you would say the house number you're at. That makes sense, right? This is comparable to that. If n tells you what orbital you're in, what street you're on, L would serve to be like your address. And some streets are bigger than others, right? My street stretches all the way across St. Catharines. It's a main road. There's probably 500 houses on it, maybe more. But then, like, I walk one street over and it's a little crescent that has 8 houses on it, right? Not every street has the same number of houses. Does that make sense? Well, as it happens, the orbital quantum number is like the house number. Yeah, that's where you're going to start to find the street address of where it is, and different orbitals hold different numbers, which we know because you already told me here that the first orbital can only hold 2 electrons. All right. So, n equals 0, L can be equal to what? Sorry, just one moment here. I just want to make sure, I'm going to double check my cheat sheet here because, as always, I rehearse my lessons, and I do this thing every once in a while when I teach this. Just every once in a while, where I switch 2 numbers right at this stage, and then sometimes when I do that, it's horribly confusing for the rest of the period. So what I'm going to do is take 2 minutes and double check myself. I know, that's okay. It has the right. I respect that. Yeah, I'm going to take just a minute and just double check myself. Because have you ever thought that you were remembering something correctly, only to discover that you had set it backwards and then you horribly confused somebody? Yeah. Great. Okay, I got it.
Orbital has only 4 energy states.
Yes. So, what we're going to remind ourselves then is this. we said that not every road can hold the same number of streets. And in fact, the highest value of L possible, the highest possible value of L is whatever orbital you're in minus 1. So, obviously, when n equals 1, what is the highest possible value of L? Very good. And is there any... We don't have to then? The only possible value of L equals 1 is... By the way, I usually write L as a cursive L so that we can see that it's an L and not I or a 1. So when n equals 1, L equals 0. In other words, in the first orbital, there is only one street or one house. You go into the first street, there's only one house. In orbital 1, there's only suborbital 0. That's the only one that lives there. Probably have a pretty nice house if you're the only house on the street, or maybe you're a terrible house. Maybe that's why everyone moved away. I don't know. But regardless, in the first street, one house. First orbital, one house. There we are. In the second orbital, though, what's the highest possible value of L? 1. So what is also possible? Very good. And then, what we're going to say here actually is the absolute value of... Does anyone remember from math what the absolute value means? No. It's the number you get if you ignore the positives, if you ignore the sign. In other words, what is going to be the other possible value here? Ignoring the value, the biggest possible number here was 0. Ignoring the sign, the biggest possible number here is 1, which means that positive 1 works, but also negative 1. In other words, in the second orbital, how many streets or houses are there on that street? How many suborbitals fit on the second orbital? 3. The negative 1, the 0, and the positive 1. Okay, who can pre-tell me what orbitals are going to be possible when n equals 3 at the third energy level?
So go negative 2, negative 1, 0, 1, 2.
Very good. Very, very good. What about when n equals 4?
Negative 3, negative 2, negative 1, 0, 1, 2, 3.
Okay, very good. This is in fact how it works. As you get to bigger orbitals, they are able to have more and more suborbitals. Now you're going to notice something though. These numbers don't quite seem to line up with these, do they? 1, then 3, then a whole bunch more than 3. 5, and then 7. So what is going on here? Well, we're going to talk about that. Because it gets a little bit... Well, we'll talk about it. Each of these subshells corresponds to a type of orbital. You can think about this as being a type of house. Does that make sense? In the first street, there's only one house, but not just that. L is a type of house. When L equals 0, we call that an S orbital. An S orbital. When L equals 1, oh, I'm sorry, am I in the way? When L equals 1, we call this a p orbital. Oh, I did it anyway, didn't I? We're going to talk in a minute. See? Every time. That's okay. We'll correct it in a minute. Every time. When L equals 2, we call this a d orbital. And when L equals 3, we call this an f orbital. Now, don't worry about those names yet, because, man, you're going to remember them just fine moving forward. Yep.
When you say L equals 1, 2, or 3, is that absolute value 1, 2?
Yeah. In fact, it's not, because in fact, the absolute value thing I'm saving for ML, I do this every time, and I just checked, and then you know what I did? The thing I do every time. Every time I introduce it, I do this. Don't worry. It's going to make perfect sense. Just bear with me. I apologize in advance. And every time. You could probably go back and watch the video of me teaching this like 8 times in a row, and every time I do this. I don't know why. It's a thing. It's become like a tick.
Well, if you're watching the same video, it's because it's the same lesson.
This is true. So now, keep in mind that if you're in n equals 1, because the only possible value of L is 0, in the first orbital, what type of orbital is present? Only an s orbital. Whereas in the second shell, you can have an s orbital or you can have a p orbital. Does that make sense? And then, in the third shell, you could have an s orbital, or you could have a p orbital, or you could have a d orbital. And when equals 4, you could have an s orbital, a p orbital, d orbital, or an f orbital. Does that make sense? You can think of it this way. It makes sense. As the orbitals get bigger, you can fit more subshells into them. It's a bit of an oversimplification, but it works. Does that roughly make sense? All right. On the next page, I gave you a copy of this diagram, and this shows you the basic space of it. And you'll see that, I wonder if I can rotate this page. Because for you, it's easy to just flip your page, but for me, well, I'm not, necessarily opposed to that, but I feel like there must be a better way. Picture. You would think rotate picture would be like a fairly common feature, but I'm not seeing it. Well, let's try this, because that's going to bug me. Yeah, OneNote's a little funky sometimes, but this way, at least you think it would.
What is it showing?
There we go. There we go. Much better. Okay, so this is showing you, I wanted to give it to you nice and big, so I put up. This is showing you the shapes of each of these orbitals. Does that make sense? An s orbital is just a perfect sphere, which means that an electron in an s orbital, really, that electron isn't actually in a clean orbit, but it's moving, and at any time it is in that sphere shape. It moves kind of randomly throughout that, but it's bound by that shape. Does that make sense? We've always thought of it as a circular orbit. That's an oversimplification. The truth is it's moving in 3 dimensions, but it's moving bound within the shape of that sphere. And the first s orbital would be smaller than the second s orbital, which would be bigger than the third s orbital, because every shell has an s orbital. Every shell has a spherical orbital. Does that make sense? Yep.
So, if an electron's orbit isn't 2D, are planets on a solar system's orbit 2D?
Yes. Well, very, very close to 2D. There's slight angles at them, but very, very, very slight. Like, equivalent if you're building it in a model this size, talking like centimeters of tilt. So essentially, the system does work in 2 dimensions, which is a really fascinating thing. And there's a lot of multi at play here. But atoms don't work in 2 dimensions. They do work very much in 3 dimensions. Yes?
Does that mean this orbital has 0 energy? Like,
not 0 energy. It's this. It has 0 asymmetry, is really what this is telling you. It's telling you that there's no axis in which this is unsymmetrical. In other words, it's a perfect sphere. So this is a measure of almost the deformation of the shape of it, and it's not deformed at all.
Is that just like its regular path?
So it will travel in a perfect sphere. Movement may be chaotic. Electrons move very chaotically. They move randomly. We can't predict where they are, but we can build a plane of where we can find them versus where they aren't found. And an electron that's in an s orbital can be found within a sphere. Randomly within that sphere, but it will be somewhere within that sphere. Yeah.
Kind of like a bubble?
That's right. Absolutely.
Then what are all the other ones? That's when it's given energy, huh?
Sorry?
Aren't the other ones when it's given energy?
Potentially, or they may just be where they normally live. In hydrogen's case, hydrogen's 1 electron is normally in an s orbital and can move up to other orbitals.
So what about other elements?
Well, they have things that live in s orbitals normally and things that live in p orbitals normally. Electrons in d orbitals normally. So a p orbital has this kind of stereotypical bar shape. It's almost like two balloons held together at the middle. And a p orbital actually has three suborbitals. One that kind of moves along, one that moves 90 degrees to it on the z-axis, and one that moves 90 degrees to it on the y-axis. So you can almost think of a p orbital as consisting of like 6 balloons, 2 moving up and down, 2 moving front and back, 2 left and right. But each of those exists in pairs. So you get a pair of electrons that move between these two states. They can be found anywhere. You have another pair of electrons that can live in this p orbital between those two. And you have a final pair of electrons that can move here. So within the p orbital, there are 3 suborbitals further still. This, by the way, where the absolute value comes in. That's the ML value. This is the thing I do wrong every time, which we're going to go back and correct on note because I'm a dummy, and I'm sorry about that. Every time. Yep.
So when we talk about an orbit, we talk about something that consistently travels around.
Mm-hmm. And these consistently travel around the nucleus.
However, if you're saying that they can be chaotic, then is it a orbit still? Or
Yeah, you wouldn't, yes, it's an orbit. That language implies to us a nice circular path. To a physicist, orbit, to a quantum physicist, to a guy who thinks about electrons all day, orbit doesn't make you think nice circular path. It makes you think motion with a center mass around which it's centered. And that's all this is. So the same idea where it's motion that has a central mass around which it's moving. And if you look, all of these are symmetrical. So they're not circular, but it's always symmetrical motion.
But for instance, a electron could just turn around, could it not?
Yep, they move. So these are all, an orbital is defined by all the places in space where that electron, in relation to the other electrons in the atom and in relation to the particles in the nucleus, will be happy and stable. And no problem. And you know how when you solve, like, when you set up a linear, so say you set up a parabolic equation, y equals 3x squared plus 2, you get a parabola, and any point on that parabola satisfies the equation. Basically, there's a bunch of forces acting on an electron. And there's infinite number of places where that electron can be stable and still be attached to those forces and still be inside the atom. But then there's also an infinite number of places where it won't be stable, where it's just not going to work. Does that kind of make sense? And this is the boundary. Any place in there that it's hanging out, it is still stable, and so it's energetically favorable for it to be there, so it stays there. If it attempts to move outside of that boundary, that's energetically unfavorable, so it doesn't happen. Which is no difference then. I am bound by this wall. I know that's weird to think, but the reason I can't move through it is because it's not energetically favorable for me to move through it. Seriously, I mean, the atoms that make up me and the atoms that make up it don't want to pass through each other. They want to repel each other, and so I can't just walk through it. Likewise, an electron, it's energetically favorable when it's hanging out in some places, and other places it tries to go there, and there's forces saying, no, that doesn't work. And all an orbital is the space where it's like, yeah, I'm comfortable here. That works. And it takes on a certain shape because it's interacting with all the other poles and all the other forces in the atom. That is really esoteric and confusing. But basically, an orbit is just the place where an electron can hang out and be stable without making the atom fly apart, and so it's where the electrons do stay out. Yes?
How does an element go anywhere in orbital? They have set states and no gradual degrading or increasing.
Again, any electron that's in anywhere in this orbital, its energy level isn't changing. It has energy, but it doesn't have a changing energy level. That's the whole point. An electron moving through there is in constant motion, and so its energy level is stable. It's at a constant energy level. Constant energy doesn't mean moving. It doesn't mean hanging out in one place. It just means not accelerating, not decelerating. Moving faster, not moving slower. If you think of it from a physics perspective, it's in constant motion. Now, it's in constant, really complex motion because it's interacting with a million other particles, all the other electrons, all the protons, at a deeper level than that, all the quarks. But as long as it's in that orbital, all those forces are balancing such that its energy level isn't changing.
So all their set states are in that highlighted area.
Bingo.
It's not like they're moving in between those states, like I'm coming from here and going.
Yep, exactly. That's right. So within this orbital, it's not moving boom, 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 spot to spot to spot. It's moving fluidly and steadily and kind of able to exist comfortably and normally, but it can't move beyond that spot without being in a different orbital. Complex, I mean, this is confusing stuff. It's going to take you a couple of days to wrap your head around it, I promise. It always does. Yep.
Is this related to why super heavy elements are unstable?
Yes, but not super related. That's more about nuclei than about electrons, though it is related. It's the same idea of forces in balance, but there it's the nuclei themselves that are unstable.
Okay.
Whereas those are nuclear reactions. Chemistry is all about electrons. Yeah.
How can an element have more than one orbital shape at the same time?
They can move past each other. Just no different than we could draw, if I felt so inclined, I could draw a circle around your desk